All right, lesson 5. So this is still part of outcome D3. This is about the mass defect. So we're going to begin by looking at how to calculate the mass of a nucleus. So the best way to talk about this is to jump right into an example. So example 1, find the mass of a carbon-14 nucleus. So if we weren't being too precise, here's what we could do. So we would look up carbon-14, or just carbon, I guess, on the periodic table. And we would find that carbon contains 6 protons because all carbon contains 6 protons, and that's because carbon's atomic number is 6. And then we would want to know how many neutrons this carbon contains. And so to get neutrons, we would do 14 minus 6, like we practiced the other day, and we would get 8. So this thing has 8 neutrons. So the nucleus of carbon-14 has 6 protons and 8 neutrons. Now, if you look on the periodic, well actually if you look on your formula sheet on the back side, it tells you the mass of a proton, and it also tells you the mass of a neutron. So the mass of a proton is 1.67 times 10 to the negative 27 kilograms. And the mass of a neutron, actually, according to your data sheet, is also 1.67 times 10 to the negative 27 kilograms. So to find the mass of the nucleus, I just have to take 6, because there's 6 protons, and multiply it by the mass for each proton. And then I have to add to that the mass for 8 neutrons. So 8 times the mass of 1 neutron. All right, and I'm going to go ahead and calculate that. So I do that and I get 2.338 times 10 to the negative 26 kilograms. Now, the problem with this is that this answer actually isn't that accurate. So all of the numbers on the back of your formula sheet are rounded to 3 significant digits, which is why it looks like these two masses here are the same. But if you actually Google the mass of a proton, and then you Google the mass of a neutron, and you look up what they really are, they're not actually the same number. They're close, but they're not quite the same. And so the answer that I've got here, like this answer, which I didn't bother to round for significant digits because I was just trying to show you the process here. That answer is okay if you don't care about being super precise, but in Unit D, we're actually going to be working with really small numbers, and when you work with really small numbers, it actually becomes more important to get more precise answers. So the way that I've showed you here is not actually how we're going to solve questions like this. So this is what I was just saying. So for nuclear mass calculations, we will be working with tiny amounts of mass, so we need to be much more precise. So instead of measuring masses in kilograms, we will usually use something else called unified atomic mass units, and the symbol for that is the letter U. So the letter U, it's just an alternative mass unit. So just like how we can measure energies in joules, or we can measure energies in electron volts, kind of the same idea. We can here measure masses in kilograms, or we can measure masses in terms of this letter U. And either way, it's still a mass. The nice thing about using the letter U is that it's a little bit more precise. So this is how 1U is defined. You don't need to memorize this because it's also written on the back of your formula sheet. But 1U is 1/12 of the mass of a carbon-12 nucleus. So a U, or 1U, is equivalent to 1.66 times 10 to the negative 27 kilograms. So here are the masses of a neutron and a proton. So if you, again, like I said, if you go to Google and you look up the mass in kilograms, if we add one more digit to our mass, we find that the mass of a neutron is 1.674 times 10 to the negative 27 kilograms. And the mass of a proton is 1.672 times 10 to the negative 27 kilograms. And if you convert those numbers into U instead of kilograms, this is what you get. And I would encourage you to actually pause the video right now and just try the conversion just to make sure you know how to do it. So just if you're not sure, to get from kilograms to U's, you would just divide by 1.66 times 10 to the negative 27. And there's no need to memorize these values. So if you need them for the diploma or for a quiz or test, it'll be given as part of the question, so you don't need to worry about memorizing. Okay, so now we're going to do example 2, and example 2 says, calculate the mass of a potassium 40 nucleus in terms of U and in kilograms. So you'll notice here, they're giving us the masses that we need as part of the question, and so let's go ahead and do this one. So to begin with, we're going to look up potassium 40 on the periodic table, and I see that for potassium, the atomic number is 19. So we have 19 protons, and because it's potassium 40, to get the number of neutrons, I'm going to do 40 minus 19, and that gives 21. So 19 protons and 21 neutrons. So what we're going to do is we're going to do 19 times the mass of a single proton, and we're not going to use the numbers off the formula sheet, okay? If they are giving you masses in the question like they are here, you need to actually use the mass given in the question. So for a proton, the mass is 1.0073 U, and then we're going to add to that the mass of a neutron, which is 1.0087 U. I'm just going to double check that. Even though it's on the board, it's just blocked by something because I'm recording it. Yes, okay. 1.0087 U. Okay, and let's go ahead and do that. So I'm going to distribute 19 in here, so 19 times 1.0073, that's 19.1387 U, and then I'll distribute in the 21, so 21 times 1.0087, that's 21.1827 U. And so adding those two numbers together, this gives me 40.3214 U. And now I'm going to round for significant digits. So when you are rounding, okay, you don't look at like 19, 40, and 21 because those are not measured numbers, they're counted numbers. So when you're trying to round for significant digits, you look at really these numbers here, and those all have 5 significant digits. So for my final answer, 40.321 U is the mass of one potassium 40 nucleus. Now, the question also asked me to find the mass in terms of kilograms, so that's what I'm going to do now. So I'll take my unrounded number, 40.3214 U, and I'm going to multiply it by 1.66 times 10 to the negative 27, because that's how many kilograms there are in every U. And so you can see the U's cancel out. And so now, if I do that, that gives me 6.693, and then it keeps going, times 10 to the negative 26 kilograms. And now we're actually going to round to 3 significant digits because this number right here had only 3 significant digits. So 6.69 times 10 to the negative 26 kilograms is going to be the answer for that one.